Okay, guys, we're moving on to the next section of notes. First, we talked about weathering, which was the breaking down of rocks. Now we're on to the second part, which is going to be erosion. All right, erosion is going to be taking those rock pieces that have been broken down, and now we are looking at transporting them or moving them as those smaller particles, as those sediments. So erosion takes those sediments that we already broke up, that we weathered, and now we have these smaller particles, and we are going to erode them and move them from one place to another. Now, in order for that to happen, there are several different parts. All right, the first thing is an agent of erosion. Now, what an agent of erosion is something that is actually moving. Okay, meaning, for example, water. Water could be an agent of erosion because it's moving, and if you drop a sediment or a smaller particle in it, those particles are going to go somewhere. All right, then you need the actual sediment, those particles. So now you have the something that's moving, right, meaning the agent of erosion. You have the sediment itself. Now you need one more thing. You need a driving force, right? And the best driving force, and this is an example, right? And excuse my handwriting, right? An example is going to be, right, gravity. All right, gravity is an excellent example of a driving force, meaning it's going to take that water, it's going to pull that water from a place that is, let's say, up here to a place that is down here, and any particles, let's say rocks that are in it, are going to move with it. Okay? So we are transporting these fragments, these particles. So what causes? Well, the first type of erosion is gravity erosion. Right? So what's this going to do? Gravity is going to cause those sediments to move downward, right? They're going to start somewhere up high, like on the top of a mountain. You're going to have rain, you're going to have snow. The snow is going to melt, and it's going to cause it to move down in essentially three ways. The first way is running water. Rivers, streams, that water is going to run over the surface. The second way is going to be glaciers. If you have water that's frozen into ice and they become these big, massive things, glaciers are going to move with the force of gravity downward on the side of the mountain. It's going to pick up sediments, it's going to transport them, it's also going to break them apart. So it's actually going to cause more weathering. And the final thing is underwater currents. If you've ever gone to the beach and when you walk in the water, you feel those underwater currents. Those currents occur. Every time the wave crashes, you feel that water moving underneath you, and you notice that the water is not clear. It's moving that sediment around. Okay? So the most common type of gravity erosion really is known as a mass movement, right? And it involves any sort of gravity and friction moving down large amounts of sediment. For example, a landslide, right? Right, or an avalanche. So we have a landslide, and again, apologize for the handwriting, right? Or an avalanche. And what you have with both of these things, right? You have, let's say, a mountain, and you have all of the sediment stuck to the side of a mountain, right? Gravity is pulling down, but friction is holding it here. At a certain point, all this is going to get so heavy, and again, whether it's rocks or snow, eventually the gravity is going to overtake the friction, and it's going to cause all of this to fall down. That is a mass movement. Mass meaning lots of stuff. So the second thing is going to be running water and streams. Now, running water is the most common agent of erosion. In fact, you could see it right in front of your own house. Every time it rains, water is going to run over the street. It's going to take all of that material that was on the street, and where is it going to move it to? It's going to move it to the sides or the gutters. After it rains, the middle of the street is always going to be clean, whereas if you look at the side of the road, the gutters of the road, they're going to be filled with sand, dirt, pretty much anything that was in the street. The water is going to erode and carry those sediments away. Now, when we have that running water and it's confined to a specific area or a channel, it's known as a stream. So water is going to run over rocks and surfaces, and it's going to work its way into a certain area. That we call a river or a stream. And when we have smaller rivers or streams that flow into larger ones, they are known as tributaries. They contribute to that water flow. Next, we have stream abrasion, right? And we talked about abrasion before, right? Abrasion is kind of like a rubbing, right? And when rocks are moving and carried by running water, they're going to bump into each other. So what happens is the larger sediments, those bigger particles, are carried down, right, by rolling, sliding, or bouncing along the river bottom, and that results in a very rounded shape. All right, so here's what this looks like. Okay, so we have, let's see, start it. Right, all of these particles are moving in this direction. Notice, right, they're bumping, they're sliding, they're rolling, right, and as they move down and further away from the source is going to be up here where the water is coming from, and it's all flowing down in this direction. But again, as it does that, we can see all these particles are going to break apart, and they become more and more rounded as they work their way towards the bottom because they are abrading, they are breaking apart. All right. Now, when rivers and streams do this, they cut a certain shape into the bedrock, meaning the rocks that they pass through, right? And it's going to be a V-shaped valley. Now, we've seen these before. Right? So as a river, right, if we start off with ground, let's say like this, if the river starts or the stream starts flowing there, eventually this is going to start working its way deeper and deeper and deeper because all of this water is going to weather and erode away those particles until you're left with something that kind of looks like this. And the river is flowing down here. Now, where on earth do we see that? We see that in the Grand Canyon. Right? This is the Colorado River. Here is the side of the Grand Canyon, and what shape is that? That is a V-shaped valley. Right? Right here is the water, right? And millions of years ago, the Colorado River started up here. Right? And over time, it slowly weathered and eroded these rocks until it's down into its current position. Here's another example. Right? Here is this river, and we can see these very steep cliffs on both sides. Right? And there is that river valley. That's your V-shaped valley as the water cuts through. So what we have is rivers and streams create that V-shaped valley, and they abrade and break apart, weather all of those rocks as they move through. Right? Now, there are several things that affect stream velocity. Well, what does the word velocity mean? Velocity is just another word for speed. All right, so stream velocity is going to be the speed of the water as it moves over the ground. So there are three things that are going to affect how fast a stream moves. First, we have the gradient or the slope. Now, what does that mean? Well, if you have, let's say, ground that is like this, or ground that is like this, which one is water going to flow down faster? Well, water is going to move slowly here, right? And over here, if I pour water there, it's going to move down this fast. Right? So that is slope. Again, we talked about this earlier. Think of it like a roller coaster. Right? This is going to be a much faster and funner roller coaster than this one. Next, we have what is known as stream discharge, and this is going to be the volume of water in the stream itself. So most rivers and streams are going to be able to flow or move faster if there's more water. More water or more discharge is going to push that water forward, causing it to move faster. Right? And then finally, we have what is known as the stream channel shape. Right? Meaning the shape of the actual bedrock. So if the bedrock is a nice clear V shape that has a steep slope, that water is going to be able to flow through here very, very quickly. But if there's other things in the way, so let's say you have a general V slope like this, but now let's say there's rocks and big boulders or other things put in the way, the water is not going to be able to work its way through. So the straighter the channel shape, the cleaner it is, the faster it's going to move. So in order of importance. The gradient of the slope is going to be very important in determining how fast water moves, followed by the discharge, meaning the volume or the amount, and then finally the stream channel shape. So this is where we're going to jump to our reference tables, and we're going to turn to page 6, and we're going to go to the top right-hand side of page 6, and we're going to take a look at the relationship, right, to particle size and water velocity. So it shows us the different types of particle sizes. So on the left here, we have the particle diameter. So these are the sizes of your particles. On the bottom here, we have the stream velocity, meaning the speed in centimeters per second. So what this shows us is these are the smallest particles down here. So these are small, right? And then all the way up at the top, these are our big particles, right? And we have the different sizes here, but we have names, right? So clay is really small, followed by silt, sand, pebbles, cobbles, and boulders. And these are the basic sizes of these rocks or sediments. So if I had, right, a stream that was moving at, let's say, 100 centimeters per second, if I wanted to know what's the biggest particle it can carry, I would go here to 100 and I would go straight up to this point, because this is the graph, and it touches right there. So the largest particle name that it can carry is a pebble. If I wanted the exact size, I would go straight over here and I would figure this out. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So my largest particle would be a 3 centimeter particle. Okay, so that's how this chart works. So let's take a look at a couple examples. So how fast must a stream be traveling to carry a small pebble? So a small pebble, here is that chart. All right, I'm just going to jump to the reference table so I could draw on it. So a small pebble. So a small pebble, here are your pebbles from here to here. This is your smallest pebble. So now I'm going to go straight down, right, all the way to the bottom. And right here, a small pebble has to have a stream velocity of 10 centimeters per second. So the water must be flowing at a velocity of 10 centimeters per second to carry a small pebble. Let's take a look at another one. What is the largest particle that a stream moving 300 centimeters per second carry? So now I'm giving you a velocity. So we jump to this chart. All right, so I'm going to come down here, 300 centimeters per second. So this is 100, right? And a little hint with this chart, whatever the first number is on this counting up is going to be how much these numbers go up by. So if this is 100, this is 200, this right here is 300. So if that's 300 centimeters per second, I'm now going to follow this straight up, right? As straight as I could possibly get to right about here, which is where it touches, right? And the largest particle it's going to carry is going to be a boulder, right? And I apologize, my line got a little crooked, all right? It's right here, that's where it should be. So we're going to touch up there in that space, so we have a boulder, a fairly big object, right? Again, same thing. What is the largest particle that a stream moving 25 centimeters per second can carry? So we'll jump back here. Right, now 25. So now we're going to come down here, and I'm just going to erase really quick so we can get this out of the way so we can see it nice and clearly. All right, so 25. So again, this is 10. We're going to go up to 50. So this is 10. It's going to go up by 10. So this is 20. All right, so 25 is going to be right here in the middle. And again, you just follow it as straight up as you possibly can. In this case, I take us to right there. So the largest particle is going to be a pebble. Right? So the largest object it can carry is a pebble. If I was asking you the actual size, right, you'd come right over here and you'd go over this way, which takes us to there. So if this is 0.1, 0.2, 0.3, 0.4, and it would be about 0.5 centimeters. So that's how that chart works. So that's how you determine how fast a stream is moving and the particles it can carry. All right. Lastly, when you have water in a stream flowing, it's not going to move the same speed everywhere. It's not going to happen. So it is not moving at the same speed, right? So what we're going to take a look at is we're going to take a look at this diagram, and we're going to label it where the stream is moving fastest and where it's moving slowest by indicating arrows. We're also going to put an E for erosion and a D for deposition. Now, we haven't talked about deposition yet, but deposition is a deposit. So erosion is the taking away and moving. Deposition is the opposite, where we deposit it. So let's take a look at the diagram. So we're going to start, the water is going to flow in this direction. It's going to start here and it's going to work its way all the way through. So essentially from left to right. So water is going to move right in this direction. Again, I apologize for the bad drawing. Now, this is what the stream looks like from above. These are three different side profiles, meaning either XY, AB, or GH. And what we're going to do is we're going to label them. But we have to picture this kind of like a stream or like you would a road. So the water is going to flow straight through. Now, where is the water going to be moving the fastest? Well, let's start. In XY, it's going to be moving fastest right in the middle. Why? Because right here, there's no bends, there's no curves. So water is going to flow the fastest where it is the deepest. Right? And now, since this is perfectly straight, there's no bends, we're going to label this up here as the same thing. Now, what do we see? If we're moving this way, Y is going to be on your left, so this is going to be Y, and X is going to be on your right, so this is X. Okay, again, this is your right, this is your left. This is what the stream would look like from the side. Now, where is erosion occurring the most? Well, remember, erosion is the moving of particles. So when particles are moved, it's going to be the deepest. So you're going to have erosion occurring right here in the middle. Now, if erosion occurs in the middle where it's deepest, where it's going to be shallowest, where the least amount of water is where you're going to have the most amount of sediment. So we're going to have deposition on both sides. So deepest in the middle. And remember, this is going to slowly get eaten away into a nice big V. Now, as we move to AB, here's where it changes a little bit. The water is moving fast as it can this way, and now it's going to crash into this side. So it's going to crash into letter B, which if we're moving this way is on our left-hand side. So if we take a look at these two, which has water crashing or eroding into the left-hand side? Remember, erosion means taking away. So that means we have to look at this one over here. So that means this is going to be B, this is going to be A. All right. Now, this is where your erosion is going to happen, and this side over here is where your deposition is going to happen. Erosion is always going to occur on that outer bend on this side over here. Think of this as your elbow. If this is your arm and this is your elbow and you fall, you're going to scrape and dig out the skin on that outer side. On the inside, it's protected. So here is that outer side. You're going to dig away over here and you're going to have this side protected. So this is going to get scraped out. You're going to have a hole. This side is going to be shallow. Now as we move to G and H, the water is now flowing this way and it's going to crash into G on this side. So obviously we only have one left. So G is on your right. So here is G. And this over here is going to be H. So which side are we going to have our erosion on? This is your elbow again. So this is the outer side, the part that you're going to scrape away. So here is your erosion. That means this side is your deposition. Erosion is always, again, going to be the deeper part, the part that's scratched or scraped away. It's on the outer side. So I know we don't have another one here, but if this water cuts up this way, it's going to crash into this. And I'm just going to change colors. But if it crashes into here and I draw a line and I label one of these as C and D, which side is the water going to crash into? It's going to crash into C, which is on the left, so I'm going to have something that's going to look like this, crashing in on the left. So this is erosion, this is going to be deposition, this is letter C, this is letter D. Okay, and same thing here. If we go this way, the water is going to crash into this. So we have erosion over here and deposition over there. Okay, so again, erosion is the moving away of particles, deposition is the dropping off. All right. Next, we have wind erosion. This is one of the last things. This occurs very commonly in deserts. So it occurs when the wind blows sand, silt, or smaller grains against other rocks, and it essentially sands them away. You see a lot of these where there is no water going on. Sorry, not a lot of rain and not a lot of water in the area. Okay. And finally, we have glacial erosion. These are where massive glaciers, which are naturally formed masses of ice and snow, and it's going to move downhill powered by gravity. Right? Glaciers. This is a beautiful example of a glacier. Right? This is all part of the glacier up top, but it is broken through the side of the mountain, through the side of the rocks over here, and it has created this nice big shape. If we got rid of this, right, that glacier is going to create a different type of valley. It's going to create a V-shaped valley. Glaciers leave very big grooves or scratches in the rocks. We're going to come back to glaciers in a little bit, right? We can see them here, right? And especially here, right? These are these scratches that glaciers move, and it tells you that the glacier flowed down from here this way and then went back up that way, right? Again, beautiful example. We see all the vertical scratching. Right? And lastly, glaciers are going to form U-shaped valleys. Remember, rivers are V-shaped, glaciers are U-shaped. Right? And here is a nice V shape. So there is no river flowing through here, but the glacier as it came through cut this U, right, out of the side. So it's kind of rounded on the bottom as opposed to a river, which would create a V shape with the water flowing right there on the bottom. Okay, and again, here is a great view of a glacial valley. Here is that nice big U that was created when the glacier, oh, I missed over here, as the glacier worked its way through, and we can actually see some of the glacier in the background over there. All right, so what that does is that takes us to the end of erosion. All right, please make sure that you create the notes, write them out, look them over before you answer the castle learning questions that go with this. Again, if you have any questions, please make sure that you ask, notify me either on Teams or through Remind if you have any questions or you'd like me to explain anything else.